Welcome, everyone. I'm excited to be here. Let's just get this set up. Today, we're going to be talking about topology for time series. So a little bit about me. I'm a senior lead data scientist with expertise in a lot of different areas. I've focused a lot on the weirder areas of data science, like time series and network science and spatial data. I'm currently finishing up my book, The Shape of Data, which will come out soon. And I'm here in Miami, Florida, where I do a lot of things outside of data science, including art and writing. So let's dive into time series data. There's a lot of different uses for time series data. Comparing trends over time across different regions or products is key for a lot of retail businesses. So we might want to perhaps look at different stock markets and how they're performing over time. We might want to look at specific products, track sentiment over time, track sales over time, track sales over time and region. We may want to forecast future sales or population. So we may want to look at forecasting population growth for metropolitan areas or different countries of the world. We may want to forecast how much impact an epidemic might have in a region to be able to plan resource allocation. We may also want to detect future changes in system behavior. So we might want to understand that the price of grain is going to spike, or that there's going to be a stock market crash, or that a public health crisis like COVID is going to eventually level out into more of a stable period of the epidemic. So there's a lot of different uses for time series data. However, looking at time series data and comparing two different systems is really difficult. There are a lot of assumptions with time series data, including a stationarity assumption, which means that your statistics with the time series aren't varying over time. You don't have these sudden jumps and dips in your data, which usually does not hold, which means that a lot of the statistical methods will struggle with real world time series data. Another assumption for a lot of methods is that you have measurements at the same time points. So if we look at the stock market comparisons graph here, you can see in 2015 and 2016, these values don't exist for our market too. And in the real world, a lot of times systems will fail in machines or in data capture systems, and there will be a gap. Two different systems might have different time periods of collection, and all of those things can impact whether or not a certain method can be used. There's also autocorrelation. So what happens tomorrow depends on what happens today, and possibly what happens yesterday. If we think about, say, weather systems or pricing of goods, it's very dependent on what's happened in prior time points. And that's something that breaks a lot of common machine learning tools and statistical tools, such as regression. This autocorrelation is a really important part of time series data. A lot of times, there's also an assumption that there aren't outliers. There's not a lot that we can do about outliers, but there are some methods that are more robust to these points. There's a nice distance geometry method called the Frichet distance that can be used to compare time series like this, where you don't have as much stationarity as would be ideal, where we're missing some of these time points, and where we do have some of these autocorrelations and outlier points. However, it can take a while to compute some of this, and we're looking at potentially a very long time series. So it would be nice to kind of have an approach that's a little bit more suited to time series. So one of the things that we can do is look at time series as dynamic systems. Basically, whatever is capturing the data is sampling dynamic systems at different or similar intervals of time within that system. From there, we can compare the systems themselves, and we can do this through using topology. There are these connections between dynamic systems and this field of topology that's able to model the components of the system underlying the time series data that we're actually seeing come from this system. So what is topology? Topology aims to look at the global properties of a space. There are a lot of different invariants within spaces that we can look at that are useful for classifying what space we're dealing with, potentially in very high dimensions. One of these is hole counting, which we'll look at in our example on the right. However, topology isn't as concerned with distances and curvature as geometry is. So it doesn't matter if we're kind of stretching or squishing the data or the space. We're not as concerned about if there's curvature or if it's very flat Euclidean space. We're more concerned with these invariant properties and being able to measure them. So if we look on the right, we can see one of the main homology examples that's used in topology, looking at how you can turn a donut into a coffee cup and turn a coffee cup into a donut. So our donut has the solid, something called a torus, the solid object with a hole in the middle. And if we start stretching it and pulling at one of the sides, we can start getting this coffee cup shape. And then we can kind of deform it to have this coffee cup shape. And basically, topology is more concerned with how many holes we have in this object. Our donut has one of these holes, and the coffee cup has the same type of hole that exists. Very different geometries on these objects, very different distances between points when we do this deformation. But at the end of the day, we have the same paths that exist. We have the same holes that exist on the object. Another example is the difference between a baseball and a football. So our baseball is solid. We don't have this void inside of it, but in our football, we do. We have air inside of it. And so we just have this two-dimensional object there. We don't have a solid fill in there. So there's a method in machine learning called persistent homology that lets us apply this sort of thinking to data. Basically, we can create a series of spaces based on the distance between points in our data set. This is called a filtration. We define different distances and we create this series of spaces where things are connected based on whether or not they're mutually within the same distance. And this allows us to analyze these holes that exist in the data at different scales. And we can do this for a lot of different features. So at the very basic level, we have these connected pieces. How many things are connected to each other? How many discrete pieces exist? How many points exist? How many holes exist? We have different sizes of holes. So we have different dimensionality for our holes. Usually we're more concerned with connected spaces when we're using persistent homology. The higher level topological features usually don't come out to play in data science very much, which is good because it's difficult to compute them. So when we look at doing this with time series, we can create this persistence diagram for each time series. So we can go through these filtrations, figure out which topological pieces exist within each filtration. And we can do this for any number of time series. In the example that we'll go through in R, we only have 2 time series to keep things simple. From there, we have this summary of what features exist for the time series, and we can apply a statistical test. There is something called a Wasserstein distance, which is just another type of distance that's out there that can compare these diagrams. There are lots of different distance geometry metrics out there that are beyond the scope of this talk, but we have a distance metric that we can choose and create a statistical test to see whether or not the features that exist between two time series or a series of time series are statistically different or not. And once we run this, we can compare it against a significance level, whatever our p-value is that we choose, and we can see whether or not these time series have the same features over the length of time that we have. We can also parse the time series into smaller chunks and look at periods of time and whether or not the time series has changed within a time series or if it's changed between the time series and that time period. This is a very flexible method and it's being used quite a bit, especially within stock market analytics these days. So before we get into questions, I'm going to go over a little bit with the data sets that we're going to use with our R code. So we're going to use some pretty simple stock data sets for this. A South African stock exchange and an Egyptian stock exchange. Roughly the same time periods, but some dates do not correspond exactly within what days things are being traded. So we do have some of those differences in when the data is collected. I think now is a good time for questions. Let me just get out of this.
Okay, does anybody have any questions? And maybe while we give it a minute, because people, if there are questions, they'll be typing. That always takes a little longer. Fatima, maybe you can share the data sets and everything in the chats. So does anybody have any questions about what Colleen just covered to this point? I feel like I need like a little clock. I have the, there we go. So Colleen, why do you prefer R to Python for time series?
It depends on what method I'm using. There's a problem with Python's persistent homology implementation at this point that requires really complicated fixes, and R has a package that you can just download and integrates really well. I'm on Windows, so the Python package is requires a different part of my system.
And are we using topological measures to compare two sequences? How similar are they?
We will get into that when we actually dive into the code and see whether or not these are similar or not.
And do you have any resources or anything to help people learn more about topology theory?
Yeah, I have a lot of talks on SlideShare. I can send that after the talk. But I've given a lot of different talks on topology at this point and put together a lot of presentations.
Okay. And how can topology? Oh, we're gonna. Where are we? Here we are. How can topology or how can topology how can studying topology be beneficial when forecasting?
So it can be beneficial in a lot of different ways. It works quite well with small data sets, and it works quite well when the assumptions are broken for a lot of statistical and machine learning methods. So when I was in grad school, I started out in psychometrics, and there's a lot of assumptions about how survey data is collected. And another grad student at my program had collected data that broke all of these assumptions with how she had put this together and how she was looking at the evolution of identity over different contexts. And using topology allowed us to be more flexible with the methods and not violate these assumptions. So I would highly recommend studying topology as well as geometry because there's a lot more flexibility with statistical assumptions if you're working on spaces rather than your more traditional modeling, you can look at the global properties rather than these local properties.
Okay, and this next question kind of plays off of that first one, which was about, why do you prefer R versus Python for topology? So which Python topology packages have had the issues?
PerSim is the package. There's a couple packages that need to be assembled to do persistent homology easily in Python. And I discovered at the last talk that I gave that there was an update to one of the packages, and there's still issues being worked out for different systems. I like Python. It's useful for a lot of things. Time series, it does not have as much support. Like SSA, it's mostly experimental packages for those applications. There are a couple time series outside of deep learning that don't exist in Python yet. R has a lot more when it comes to time series.
Okay, and this is going to be the last. We have more questions, but this is going to be the last one I ask before we get to the practical side of things. What's the difference between radionics and topology?
I've never heard of radionics.
Let me make sure. Oh, what about, okay, there was a correction. Radiomics?
I've never heard of that either.
So
it sounds like it might be something related to radiology, which is a medical field.
Jorge, sorry, we don't know. Okay, so let's continue on to your practical side of things, and then reminder: any questions that you have, we'll answer them all at the end. So yeah, let's continue.
Sounds good. I will share this, and we'll pull up R. So this is R. One of the things that's going to be important is that we set our directory. So you can go to File, Change Directory. I'm on my desktop. That's where my data lives. So we're going to change it there. You may have to install some packages. There's an easy way to do that under Packages and Install Packages. It'll ask you to give your location, and then you'll have access to a list of all of the packages that exist in R, and you can download whichever ones you need to use from there. So we're going to get our data into R. One of the things that we want to do is scale our data because the size of the markets varies, and we want to look at the differences in trend rather than the differences in scale. So we're going to get both of these into R. We can look at what the data looks like a little bit. So the summary function will tell us kind of our mins and max. It's not as useful for time series, but if you're working with other data, this can be a really handy function to have. We can also do a very basic plot that shows us kind of what the trends look like. So we can see that there are some overall trends and then a lot of noise between time points. We can also look at our Egyptian Stock Exchange data. So we do kind of see some potential differences here, but we do also see this dip, and we kind of see that M shape that we saw in our other data. So not really sure how this is going to come out, if we're going to have something significantly different or not. Might be. One of the important things that we do is create this distance matrix. We're just going to use Euclidean distance here to get our distances between points within our time series. So we'll do that. And then we'll load our TDA stats package that we're going to use for this analysis. Again, if you don't have this, you can go to Packages, Install Packages, and search for the TDA stats package to install it on your system. So we'll load that. Looks like it's in there. And then we'll create this filtration based on distance for both of our time series data. So we're going to use the Vittorius-Rips complexes, which has a little bit more relaxed requirements with which points are considered within a certain distance of each other than some of the other methods that are out there. It just helps us compute this a little bit more quickly. We don't tend to lose much using this method. So this calculate homology function is the core of what we're doing. So for each of these, we want to make sure that we have our proper data and that we have the same dimensionality. For this, it starts at 0, so the 0th homology and the first homology group. We're only going to compute 2 of these. In practice, that's about all you need when you're working with this method on real data. And then because we have a distance matrix, our format is this distance matrix. So we'll compute this for both. It won't take very long. As you get more and more data, it's going to take longer to compute all of this, but we have pretty small data, and a lot of time series data, it's going to be pretty small. So we can make a nice plot of our information and look at this persistence diagram for our 0th homology, our connected components, and our circles, which is the first homology group. So let's look at our South African one first. We can see that we only have these connected components. We have pretty strong separation here. These are just different connected components at different distances that we used. So this is pretty typical. We have some grouping and a lot of things that are pretty clustered together. You can look at our Egyptian one here. This is a lot more spread out. So our points tend to be clustered right on top of each other, but they aren't as close to each other with the distance filtration as we saw with our South African one. So based on this, I would say that we're probably going to find a significant difference. And again, we only have these connected components. We don't seem to have any circles that exist in our data. So we can calculate this distance, this Wasserstein distance between diagrams with this function. And we'll get a nice number out of that. For a lot of papers, you'll want to report what this distance is, as well as the results of your statistical test on it. Doesn't mean a whole lot until we do our permutation-based statistical test. But this is a nice way to get the numbers and what they actually are. We can do our permutation test, which has this parameter of iterations. So we have our persistence for both of our data sets. So you'll put that in, and then the iterations is just the number of times that you want to permute to compute this statistic. Right now I have it set to 25. That's probably as low as you want to go. As you get more iterations, it's going to take longer to compute. But this is probably okay for our demonstration. So this is going to give you a lot of output. So we have our dimensionality. We have our 0th homology group and our first homology group. These are the permutation values that we got, the distance that we got, and our p-value. So our p-value here is less than 0.05, which is where we usually set it as the significance threshold. So this does suggest that we do have differences in the time trends between our 2 time series. This is not applicable because we don't have any of these features in either one, but if we did, we would also have a p-value here to see if there's a difference in those in that dimensionality as well. So this is essentially what you would do to compare 2 time series. If you have more, you can compute more of these permutation tests between the diagrams that you get for as many time series as you want to compare. One thing to be aware of if you're working with a large number of time series and doing these mutual single comparison tests, you'll want to use the Bonferroni correction to adjust the p-value for significance so that you don't end up with these false positives. So that is how we compute these differences. I'll get out of this and we can go to some questions.
Colleen, maybe you can keep it pulled up because there's a question about the,
Okay.
and I'm probably not going to say the whole thing, right? The FOM distance. And what is that getting at? How do we interpret the value of 1.54?
Okay,
Yeah.
so this is computing the distance between the diagrams. It doesn't have a whole lot of meaning on itself. It's just another statistical number that's out there. But it gives us a basis if we're reporting for a paper, basically, of what the statistic is and then what the p-value is for that. We can get confidence intervals. We can derive all of that to see where a random iteration of this would land versus what our two data sets suggest.
Okay. And there's a question about what's the last correction you mentioned for p-value. Somebody in the chat said it was Bonferroni correction.
Yep,
right?
Bonferroni correction, which if you're running single comparisons across a large number of data sets, basically you're upping your chance of having a false positive by random chance. So you want to correct which p-value you're using as a cutoff score. So if you're using p equals 0.05, our usual one, and you have 5 different comparisons that you're doing, you've just upped your chance that one of these is a false positive. So if you divide it and use, I think it comes out to p equals 0.01 or below, that would be an equivalent, basically the equivalent way of doing it, given that you have all of these other chances for a false positive.
Okay. And then Alan wanted some confirmation that the two time series at confidence level 0.04 are different shapes. Is that right?
Yeah. Essentially, they have a different topology from each other, which, given the connection between dynamic systems and topology, you can look at the topology of a dynamic system. It essentially means that they're coming from different systems. There's something else underlying the measurements that you're getting. They're essentially, what we've got from our p-value suggests that they're coming from different systems. There are different things influencing them, which we would expect. There might be some correlation between what happens in South Africa and what happens in Egypt, but they're pretty independent systems. If we were looking at, say, 2 US stock markets like NYSE and NASDAQ, we'd probably see more of the same underlying system because you have the same influences of politics, country finances, those types of things.
Okay. And Julio is asking, what is the hypothesis that is being tested?
The hypothesis is that we have the same underlying system, and this suggests that we don't have the same underlying dynamic system controlling these stock prices.
Okay. And we have another question about if there's a more efficient method other than topology to make this comparison.
There are ways of doing it with the Fréchet distance given this data, but it's going to essentially be the same steps. You're going to be looking at these distances, creating a permutation test, And that does not exist in a package in either R or Python. So this is a bit easier to work with, given that there's already a package. However, given that we have different time periods and we're breaking a lot of statistical assumptions, there are a lot of time series comparison methods that aren't going to work here.
Okay, and then we have some leftover questions from the theory side of things, so I'm going to answer them, or not. I won't answer them, but I'll ask them.
Okay.
So, could any data be used for time series, or is there something specific that we should use?
Well, you either have time series data or you don't. You either have data that's collected over time or you don't. Anything that's collected over time can be turned into a time series problem, but if you're not looking at anything over time, you don't have a time series.
That makes sense.
It's basically this autocorrelation. You have time periods that influence each other, and that's essentially time series data.
And which model would be, and I'm hoping this is relevant, which model would be suitable for data that has no stationary?
Generally, you're going to want to use something like topology or geometry, because the stationarity even underlies deep learning methods like LSTMs. They still have the stationarity assumption that the statistics and what you're computing locally holds over the global properties. Essentially, we're cutting out the local properties where all of this stuff can go wrong and just looking at the global properties.
Okay, and very well, off-topic question, but do you have a preferred source for learning R?
I learned by Googling. So there's a lot, Python and R have fantastic free resources on just about every data science blog and a lot of free PDFs to help you get started for data analytics.
Yeah, Data Science Dojo also has free tutorials on R and Python. So, but Googling is a good place to start. Going back to our practical example, are there any transformations required besides scaling?
No, you shouldn't need to do much. One of the things with time series, usually there's some sort of integration step that deals with the stationarity, but because this method does not look at these local properties or compute anything statistically besides doing the comparison at the end, you don't have to worry as much about that. One of the things with topology in general is you have scale invariance, you have robustness to outliers, and a lot of the things that you need to do before you use a statistical method or certain machine learning methods generally don't apply to topology, or there's not as many of them that you'll have to do if you use a topology-based method.
Perfect. And last question is asking if, or I guess we have more than one question, but will the recording be sent to us later? Linda, yes. If you're in Zoom with us, that means you signed up through our website and we will send you an email. Otherwise, it'll be on our YouTube channel. It'll be on Data Science Dojo's website. We'll share it on social media, so there should be plenty of opportunities to find it. And I'm gonna butcher this one. So, have you ever tried? Is it Giotto?
Yeah, I've used that a couple of times. It tends to be a little bit more complicated than the R package. And again, there's some steps that you need to do to make it compliant with Windows. I found a lot of the topology and geometry packages in Python, depending on what update they do, you may or may not have to do a lot of backend installation to get things to be compatible again.
Perfect. All right. So that's all the questions we had. So